Okay, good afternoon from Spain. Sorry for the little delay. First of all, I would like to thank you for your time and your attention. I hope you really enjoyed this webinar, and I cross my fingers to not have any IT issues. Okay, my name is Patricia Romero. I'm the Simulation Solutions Commercial Manager. In the backstage, we have the support of Cristina Lázaro. She was involved in the development of these power plant, diesel power plant simulators. And now she's the project manager of the contract for maintenance, modernize and upgrade all the Spanish diesel power plant fleet. Additionally, we have the support of Jesus Galvan. He's one of our best instructors, and he has been training or teaching in all of these OTS, Operation Training Simulators. Okay, let's start. Okay, for those who don't know us, Tecnatom is an engineering company and it's a group, an international group, headquartered in Spain, but with subsidiaries in countries such as Brazil, Argentina, Mexico, USA, or China. We are mainly focused on generation sector in three main areas. One, inspection. Another one is training, and the other one is a digital operation. Inside this digital operation, we can find simulators and digital twins, but also control rooms and monitoring centers and operating aid systems and assets management for the facilities. Regarding simulation areas, in Tecnatom, we have been offering for more than 25 years simulation solutions in order to improve the safety, the operation, and the efficiency of fossil fuel-based power plants. Our differential values are that our knowledge of the power plant operations is translated into our products, into our simulators, giving a product that is very precise and very accurate, focusing on what really matters from the point of view, from the operator point of view. Okay. Another differential value is that we are not only developers. We also can operate the simulators even in remote way, and we can provide the qualified instructors if the customer hasn't got them, and we can train the future trainers. Is another option, and we provide consulting services. We do the maintenance, the upgrading, and the modernization of the simulators during all the life cycle of the simulators. Okay, now let's move on to the topic. Here is the agenda. We are going to talk about 18 minutes more or less for these topics. You can see here. And then we are going to see 18 minutes of demo. We have prepared a video. I'm sorry, it's too long for this webinar, but don't worry, we are going to share it with you completely. Okay, for the questions, you can feel free to answer questions. Sorry, all the questions you have during the webinar. We are going to answer it at the end of this webinar. We have reserved more or less 9 minutes to do it, but I compromise myself to answer every single question and share with you. Okay, so we are going to talk about the challenges of the isolated electricity system. Most of you are aware of that challenges, but I want to emphasize the critic that these systems are, or the critic and the fragile of these systems. First challenge of the isolated system is the stability. I think is the major problem. This is because the isolated electricity systems are relatively small systems equipped with small generating units that offers low inertia. That means that frequency variation in the grid has stronger effects on the system than those that suffer the more big or the more interconnected system. Okay, another critical point is the messing of the grid. These systems usually are little messed and usually have to work in a low voltage level, and also the power of the source circuit are also lower. So we have to protect the systems better, and they are more vulnerable. Another challenge for these systems is the power reserve margins. Due to the insulation of the systems, the power plants have to work or to operate in a lower power load, in a lower power level, in order to face the peak of the electricity demand that could happen at a time, because sometimes there are no other option. So the power plants needs to be flexible in order to deal with that situation. For example, in Spain, in the island systems, this reserve margin goes from 40 to 70%, while in the peninsula, in the mainland system, the reserve margin is just 10 to 15%. So we have high power reserve margin in these systems. Another challenge is the maintenance or the operative cost of this kind of systems. The reasons are multiple. Well, first of all, we can say that the economy of scale cannot be applied in these systems, but there are also another costs. For example, the cost of the fuel, the transport of this fuel to a remote isolated areas, or for example, the maintenance is not the same. The climate or the environmental conditions are not the same as in a mainland system. So these systems must be very careful with the cost control and with the efficiency of the plants. Okay, another challenge of these systems is the renewables energy sources penetrations and the storage systems. This is to face with the target of 2015 decarbonization targets. And this integration of new systems or new resources are going to change the operating philosophy of some power plants. For example, diesel power plants that now are working in a base load are about to change, and they are going to operate in a backup or as a reserve power source. In these cases, OTS cover even more importance, because the personnel must be well trained, and the training should be made in a simulator in order to guarantee the quality of the supply when it is needed, because in those cases there are no other resources. Okay, and at last, another challenge for this kind of systems, but also for the mainland systems, is the modernization and digitalization of the grid to respond to the interconnection of the system. For example, the digitalization of the operation and the services of the electric grid, maximize the distribute resource integration capability, the development of new mechanisms in order to integrate all the agents of the system. Also to integrate a new power consumption, transport, mobility, or heating, ventilation, and air conditioning systems. And at the end, go forward. Okay, now let me explain you the benefits of simulators, not only in training, but also in engineering. Here, I would like to speak about EPRI. EPRI is the Electric Power Research Institute, which carry out a cost-benefit analysis of simulators used at fossil fuels power plants. And they identify benefits such as availability savings, thermal performance savings, component life savings, and environmental compliance savings. Additionally, they reported that approximately 20% of forced plant outages were a result of an operator or a maintenance error. Therefore, reducing operator controllable outages through training on simulators can significantly reduce the operating cost. Our simulators are recognized worldwide as a realistic method to provide real-time and hand-on training of operators, but also can be used for validate procedures, those we have, or new ones. We can conduct studies, engineering studies on them, okay, and could serve for supporting the training of other power plant personnel, okay. Simulators at the end are cost-effective solutions to address security of supply, to firm capacity and operational challenges in the short term. Okay, now I would like to tell you about our success story. This is the OTS we have developed. In this case, our customer, within the framework of its plan for optimization of reliability in the generation on non-peninsular electrical systems, awarded Tenatom a pioneer operation training simulator in a diesel power plant. This simulator was first of a kind and was a real success story due to its contribution to the availability of the reference plan of the real plan. Okay, what are the characteristics of this OTS in this diesel plant? Okay, here the simulator includes the simulation of the control systems, the human-machine interface, and the process in real time with TeamSuite. TeamSuite is our technology, our simulation technology. Okay, we have developed all the simulator with our own technology. Okay, the SCADA is in this case, and I say in this case because we can choose another options, but in this case we have chosen the stimulated way. It was a real high fix from General Electric, and is stimulated means that the real system, the same as that one is in plan, is directly connect to our simulation. Okay, but on the other hand, all the logic and control of the plan that was in the real plan with PLCs from Siemens is completely simulated. Okay, the scope of our simulators covers interactive virtualization of local electric panels, cover all power plant systems, the simulation of all power plant systems, but not essential systems. They have numerous malfunction of switches, pumps, valves, whatever is simulated can be fail. So the scenarios are very rich in those cases. Okay, we have also simulated remote actions such as local gas turbines controllers. For example, in this case, are from ABB. We have simulated local maneuvers in diesel groups or electric local panels, maneuvers carried out by the power grid operator, not for the operator of the power plant, but for the operator of the grid. And we have everything, I say, is included in our simulator and is controlled through the operation displays by the operator and through the instructor console by the instructor in this case. Okay, and we are in the demo. You can see the instructor station and also the operating displays. Okay, these simulators at the beginning were the main objective of them was to train the recovery of after a blackout situation. Okay, but the scope is much bigger, and we can train on them other incidents because of the quantity of malfunction we have simulated, but we also can train the standard operation, the startup or of a group in a normal situation following the procedures. Okay, and this is a strong point to make the operation homogeneous among all the operators. And also I have mentioned before, we can use it for engineering purposes. Okay, now let's focus on the real impact on plant availability. Here we developed our first simulator. It was a pilot experience, and we measure times. Before using the simulator, the blackout recovery time was about 400 to 700 minutes. After training operators in the simulators, the recovery time decreased to 70 to 100 minutes. That is about 80% less of unavailability time. Okay, so you can see here, if we make our thoughts and we know how the megawatt cost, well, we can see that is a great benefit. But the most direct economic benefit is the reduction of penalties in our Spanish system. The lack of supply, even and more important in a remote island, when there are no other options, there are penalties, and you have to guarantee the quality of the supply. Okay, but there are another costs, such as non-production costs, of course, but another as a social impact or public image that are also very important. Here you can see that the return of the investment was demonstrated during the first blackout after the training. So we have the recognition of our customer, and the result of that was that he wanted to continue the experience with us, and we developed 8 more simulators, one for each existing electric isolated system in Spain. Here you can see all our simulators and the reference plans, and also in the news, local press, promoting our Pioneer simulator. But we have also the public recognition of the, let's say, the media or the public. Okay, and this project received the award for best practice in digitalization and the second ABB, the Sustainability Excellence Club Award, which recognizes the use of the digital technologies to improve the competitiveness and sustainability. Okay, next steps toward the digital twin. Up to now, in Tecnaton, we have developed simulators for hydroelectric power plants, for solar thermosolar power plants, also for diesel power plants. So the challenge here is not simulate an isolated power plant, such as photovoltaic or aeolic plant. We have also simulated critical facilities, for example, airports. Here you can see in the slide the high voltage cabins to train maintenance operators in an airport when the blackout situations are critical as well. But here the challenge is to involve all of these isolated simulators in a complete grid simulate it with the transmission, with the distribution, with the consumers. And then once we have this simulation base, we can connect monitoring services. We have connected to the reality. We can connect for manage all the quantity of data that are there. So that is the next step towards the smart grid concept. Okay, now we are going to watch the video, the demonstration in our real simulator. Here I explain of the sequence. I'm afraid we have no time to watch it completely, but as I say before, we are going to send it to you, and you have here the explanation. We will start from an initial condition. Okay, we have introduced some alignments to avoid the automatic startup of the emergency diesel by minimum voltage. We have also blocked some automatic connection from of auxiliary equipments for group 15. We are going to see it because we want to force the operator to start up the diesel, the emergency diesel, and also the group 15 in a manual way. We are going to provoke a transient to lead the plant to a blackout. Okay, and then we are going to recover the situation step by step, following the procedure. Okay, now I'm going to, I'm going to show you the video. I'm searching the video. Okay, here we go. Okay, here you can see the initial condition. We have a typical power plant situation with 4 diesel groups working, giving 28 megawatts to the grid. Okay, and we are going to introduce a malicious maneuver. Okay, this is a wrong maneuver. We are cutting the seawater supply for the cooling system in order to force the blackout. This is, here you can see how the plant is evolving. Okay, you can see how the temperatures are increasing in lubrication. This is the lubrication group 13. Okay, minutes after that, we are going to have a trip due to the lack of cooling. Here you can see the temperatures are in red color because they have reached their limit value. Okay, this is to show you that we have not only the logic and control simulated, we have also the dynamic of the models, and they are evolving in the similar way that in the real plant. Here you can see that we have reached 70 degrees, sorry. We are going to the engine and we are going to check the main cause of the trip. In this case, it's not so clear, but it's high temperature in the cooling water. It was the first cause of the trip. Okay. If we are going to our one-line scheme, we can see that we have no power, we have no voltage, and if you can see 45 Hertz is because it's the low limit of the instrument. The range is the range of the instrument. Now, the diesel group should be start up automatically, but I have mentioned before that we have blocked it. We put the diesel in a manual local mode. And now the operator has to realize that the diesel is not started, and he has to order to the local operator to go there physically and start up it manually. Here you can say motor parado means motor off, engine off, sorry. And what we have simulated here in the instructor console is the local maneuver of the local operator, okay? We are physically simulating physically the startup of the motor, of the engine. Here you can see engine, motor funcionando, that means engine on. Here you can see how we have a frequency. We are right now in the peak, in the frequency peak. And here in the graphic, you can see the trend of what we have missed during this time lapse while we were starting up the engine, okay? So now we have our emergency diesel started. And what we have to do now, we are resetting alarms. We are checking that the group switch is closed. It closes automatically. And what we have to do is to restore or recover the voltage in the electric bars. For doing that, we have to close one switch, in this case 5215 GDE. In this case, this maneuver should be done again locally. So our instructor is going to close it. The main control room operator has to order that. So our instructor is following what the main control room operator says, according to the procedure. Okay, here you can see that our switch has closed, and the next step is to supply voltage to the next electric bar for group 15 in order to have auxiliary components, okay? In this case, we do the maneuver from the main control room. Okay, now we have supply, electric supply for group 15. This is our engine, our diesel group. Here we are going to reset the main cause of the trip. That was the high temperature of cooling system. Okay, and in this case, as I mentioned before, we have blocked the automatic startup of several components. For example, here you can see the cooling system with water, and the operator has to connect the pumps for the correct cooling of the diesel. Here you can see that we are connecting all the equipments. You can see how the parameters are evolving. Okay, the other components are redundant, so we don't need to operate on them. Okay, in this case, some of the components are correct, but the other must be operated. Here, the operator is following the procedure. Okay, it is supposed that he or she has to check the state of the components and do what the procedure says. In this case, we are going to put in auto mode the pumps, the lubrication, for lubrication the cylinders. Now we are going to the fuel supply. We are going to connect the pumps for the gas oil supply and also for the fuel oil supply. We have to reset the disturbances that could be. You can see how the pressure is evolving. Okay, we are going to check the ventilation and now the alternator. And we are going to connect the hydrostatic pumps. And the circulation oil pump. Okay, with all the auxiliary components with correct alignment, we are going to check if we have the requirements for starting up our diesel group. Okay, in this case, we are going to ask the local personnel once again to rearm the local protections, to connect, in this case, the QC regulator for the group, and going and reset the trips in relays 86. Once again, we have simulated local maneuvers. Okay, we are going to check the requirements for the starting up. And we are going to start the group in the sequence mode. We are going to start the sequence. Here you can see secuencia activada means activated sequence. And you can see motor arrancado, that means engine on. And you can see how the speed of our engine is increasing, okay? Now, okay, I'm going to advance a little bit. Okay, once we have the nominal speed, what we have to do now is to coupling our group to the bar. Okay, in this case, we have order to the operator. Here you can see in the graphic the trend that we had missed during this time lapse. Okay, is the speed of the engine. Okay, and we check the one line scheme. You can see that our group is connected, and what we are going to do right now is to connect the excitation system. We are going to close the excitation switch. Now it's switch. You can see how the frequency is evolving, how the speed of our engine is increasing. Okay. And what we have to do right now is to adjust the frequency in manual mode, because we have asked that to the operator. Okay. So you can see how we are adjusting in manual mode the speed of our group. In this case, we don't need the synchronoscope because it's a dead bar. Dead bar means for us that it's a bar without voltage, so we don't need the synchronicity in this case. But well, we are doing the maneuvers in a proper way, just in case. Okay, now we have the speed. We are going to close. The switch. Okay. And now we are going to recover voltage in the normal bars. Through the, okay, we have voltage closing the line switch Here you can see in the one single scheme that we have the group already there. And what we are going to do right now is to give supply to the next bar, closing the switches, in order to start up the 14 group. Now, in this case, we are going to start up it automatically. Okay, we didn't block anything in this scenario, but the operator doesn't know. He has to check it. He has to reset the main cause of the trip. He has to check the water system for the cooling. Okay, he's checking. He's checking the alternator. Okay. I'm going to advance a little bit. Okay, now we are asking the local operator to connect the QC regulator to rearm local protections. Okay, well, I'm so sorry, we have to stop here. Okay, you have to see the video, the demo, because it's very interesting. At the end, you are going to discover how we recover the situation, how the simulator is evolving. Okay, and time's up, and it's time for the questions. So I don't know if we have. Let me. Okay. So now here I am. Okay, we are going to check if we have questions. Okay. Published. Okay. Okay, we have one. Apart from the good results in the time recovery, what are the differences between an operator who has trained the blackout from scratch with the OTS and another that has not? Okay, apart from the recovery times. Well, I can say that the operators who have trained with a simulator at the end are more confident. Obviously, they recover the situation faster, not only in a blackout. They know better the cause effect in its plant, so they have a deep knowledge of the situation. You can also speed up the training, and they are more confident. They have a more deep knowledge of what is happening in its plant. They have trained in a very complicated situations, so what the situation in a real plant at the end are easier because it's very uncommon to have a lot of malfunctions in sequence. So at the end, the operators are better qualified, are confident, make a better operation on their plant, so the equipment suffer less. Okay. And I think the operators are very happy training in our simulators. Okay, I don't know if we have more questions. I can see. Oh, okay. I don't know if we have more questions. Okay, more. What is the typical delivery time of one simulator? Okay, well, it depends on the plant. I mean, it depends on the size of the real reference plant. It depends on how many diesel power groups we have to simulate. Is very important the distribute control system we have in the plant. and it's very important the technological approach. Is not the same is not the same time for a stimulation that for a complete simulation. It takes longer, but at the when we simulate, the price of the simulator is lower, so we can make the balance according to the requirements of the customer. But for this concrete example, for our Spanish diesel power plants, the first prototype, the pilot experience, let's say, take us 1 year of delivery time of supply time at the end. It was the first of a kind. For the rest of the 8 simulators, it takes us between 9 till 6 months. Where this was because we learned some lessons that we apply in other simulators, and at the end we master how the plants work, so we go faster. In this period, we have to receive the data from the reference unit. We have to collect all the information for making our models, simulated models, but also we have to create them, validate it, contrast them with real data plant. So I think it takes less time for the big effort that is behind. Okay, I hope I have answered your question. Okay, I don't know if we have time for one more. Okay, could you replicate PLCs different from Siemens technology? Yes, we can. We can, and we do. We have replicate distributed control systems from, for example, ABB. This for combined cycles. We have simulate from thermosolar simulator Metso. Metso distribute control systems. We have simulate Siemens for nuclear sector. So the answer is yes. Well, time's up. I'm so sorry. I hope you have enjoyed this webinar. I hope you find all the information interesting. I'm going to check all the questions because I see there are some of them, and we will send the questions to you. And so happy to be with you today, and health for everyone. Thank you very much.